So this graph represents if I have a car that's traveling at a steady, constant speed of 60 miles per hour, and he travels for 4 hours, how far is it gone? 240 miles. How'd you get that?
60 times 4.
So it's his speed times the amount of time he's traveled, and that gives us 240 miles. Now, if I look at this on the graph, I see that the height here of this rectangle is 60. The base is 4. So when I multiply 4 by 60, what I find here is the area of this rectangle is 240. Okay, well that's great. If it's a geometric shape that I know how to find the area, wonderful. But not all functions are going to be like that. What if we just have some random function and we want to find the area under it? So let's pick some limits to bound this curve so that I can find a shape that I want to find the area of. So I want to find the area beneath that function with a base of the x-axis and then bounded by the lines x equals a and x equals b. Well, how are we going to do that? That's not a geometric shape that we have a formula for. What we can do is we can separate our function into a bunch of rectangles, because we know that the area of a rectangle is base times height, and we can estimate the area of the curve by finding the area of all those rectangles. Okay, I have a function here, f of x equals x squared, and I'm bounding it between 0 and 1. So from here to here, and I'm going to use 4 rectangles to estimate the area under the curve, above the x-axis, and between 0 and 1. We're going to do this a couple of different ways. The first way here I'm doing it is I'm using right endpoints to find the heights of my rectangles. So what I mean by that is for this rectangle here, we're going to pick the right side of it to find the height. And then for the next rectangle, we're going to pick the right side of it where it matches up with the curve to find the height. And then here and here. Now, the base of each of these rectangles is the same. I've divided between 0 and 1 into 4 rectangles. That means the base of each one is 1/4. So we're going to estimate this, and we're going to call it R4 because I've got 4 rectangles and I'm using the right-hand side of the rectangles for the height as 1/4 times, well, what's the height of that rectangle right there? Well, I get it by plugging 1/4 into the function. Okay, my function's x squared. My x value at that point is 1/4. Then we go to the next one. I have a base of 1/4, and then I'm plugging 1/2 into the x squared. For my next rectangle, we're going to plug 3/4 into the x squared. We have a base of 1/4. And for my last one, base of 1/4 again, and the height, when we plug 1 in, we square it, we get 1. If I plug all of that into my calculator, so I don't want to do it by hand, I'm going to have to find common denominators, I will get 15/32, which is approximately 0.46875. Okay, so this one has rectangles drawn with the left endpoints of the rectangles. So that makes my first one have a value of 0 for the height. My second one is actually going to have the same height as my first rectangle when we did the right-hand side, but so it's going to be 1/4 squared. The next one will be 1/2 squared. And my last one, it's not going to go all the way up to 1 now. It's going to be 3/4 squared. So we'll say this is the left-hand side of the rectangle sum with 4 rectangles is a base of 1/4 times the height of 0 plus 1/4 times 1/4 squared plus 1/4 times 1/2 squared plus 1/4 times 3/4 squared, and that gives me 7/32, which is approximately 0.21875. Okay, on the right-hand side, we got 0.46875. On the left, we got 0.21875. Where do you think the real area is? Somewhere in between, right? And it's not necessarily the average. It would be the average if there was a constant rate of change for our curve. But you know, if we took the derivative of this and we drew the tangent line, those tangent lines would have different slopes as we move along the curve. So average will get us closer, but it won't be exact. Okay. Is there another way I could draw my rectangles that might get us closer?
In the middle.
The midpoint, right? Let's try that.
Quick question.
Okay, so we're going to try the midpoints. That means I need to know what these x values are here in the middle of my rectangles to find the correct height. So that's 1/8, that's 2/8, this is 3/8, 0.5 is 4/8, this is 5/8, 0.75 is 6/8, that makes this 7/8, and then 8/8 is 1. So that one's kind of hard to see, but here's what my rectangles are going to look like. So I'm going from the middle of the rectangle up to the curve. And drawing a rectangle. Okay, so when we did the right-hand side, our rectangles were above the curve and we had extra area. When we did the left-hand side, they were below the curve. And I didn't have enough area. When we do the midpoint, I've got some below and some above, so hopefully that will offset and give us a better estimate. So we're going to call this M for the midpoint and 4 for rectangles is 1/4 times all of my heights. And since all of the widths are 1/4, I don't really need to write each term separately. I can pull it out front, right? So I've got the base of 1/4 out front, and then my heights, when I square 1/8, I'm going to get 1/64. When I square 3/8, I'm going to get 9/64. When I square 5/8, I'm going to get 25/64. And when I square 7/8, I'll get 49/64. That gives me 21/64 when I simplify the fraction, which is approximately 0.328125, which is in between the other two areas we found for estimates, right? And it does look like it's probably a better approximation.
Take average on three. Go left to right and then.
I think I got a better method. What if I use more rectangles? Okay, it's more work. And this graph has both the upper and the lower, so we had an overestimate when we did the right, and we had an underestimate when we did the left, or all of the rectangles were above the curve. They call that an upper sum. And when they're all below, we call it a lower, but it's the same thing as left and right. So both of these are on this same graph. But notice, if I look at the pink ones, and there's 8 of them, there's less error. Right? It's still under predicting, but there's less under predicting. There's less area there that's making the estimate inaccurate. And when we over predict, when we do the upper sums, there's also less error above the curve by having more rectangles. So let's look at what is the calculation if we use the right-hand side. And I've got subscript 8 there because I'm using 8 rectangles. Well, now I've divided 0 to 1 into 8. So the base of each of my rectangles is 1/8 times each of those heights. So I'm going to get 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, and 7/8 as each of my x values that we have to calculate the y to go with it. So from the right-hand side now, I'm looking at that point right there. So I'm going to get 1/64. And then we're going to plug in the 1/4 to get that point. We get 1/16. Then I plug in 3/8 to get that y value. I get 9/16. Plug in 1/2 to get that y value, and we get 1/4. Plug in 5/8, get 25 over 64. Plug in 3/4, we get 9 over 16. Plug in 7/8, we get 49 over 64. And for the very last one, we just get 1. This gives me 51 over 128, which is about 0.3984. So the first time we did the right-hand side and we only used 4 rectangles, we got 0.46875. Now I've got 0.3984. We're getting closer to the one we did with the midpoint, right? And we've got less error. Okay? If we do the left-hand side, again, I'm going to have the base of each rectangle is 1/8. And now I'm starting here. So I have a height of 0. And then I really don't have to do the calculations again because we already figured out the y values for all the rest of them. We just won't be using the 1. So I've got 0 plus 1 over 64 plus 1 over 16 plus 9 over 64 plus 1/4 plus 25 over 64 plus 9 over 16 plus 49 over 64, and that comes out to be 35.
You said 9 over 64.
Okay, you just corrected me. This one right here should be over 64. And that matches that one. Okay, so all of it came out to be 35 over 128, which is approximately 0.2734. So by having more rectangles, we're seeing that our areas are getting closer together when we do the left and the right. Okay, I'm not calculating this. But this is to show you.
So you can just get finer and finer and finer to get
Yes, the more and more rectangles I use, I have less and less error in my estimate. So that first graph, n equals 32, and we got an upper sum of 0.35 and a lower sum of 0.32. You see how my two values are getting closer together? Then I did one for n equals 100. My upper sum is 0.34. My lower sum is 0.33. What do you think we're approaching here? Something in between 0.34 and 0.33, right? Okay, and there's way more decimal places to these.
So
But,
what would be an acceptable amount then for a test so that we don't waste?
oh, I will tell you.
Okay.
I will tell you to do the estimate with n equals 4.
Okay.
Or n equals 3, or even n equals 2. I will not say n equals 32. I won't make you do that by hand. Okay, so what are we saying here? We're saying the more and more rectangles I use, the better my approximation. Is there a way I can use limits to express that? What are we looking for here? The limit is what goes to what will make this more accurate.
X to infinity.
As n goes to infinity, my number of rectangles, right? So we're saying that the area is the limit as n goes to infinity of the right sum, and as n goes to infinity, that will match my left sum. Okay, so back to that curve I had earlier. And I went back to this one because, can I call it upper and lower now? If I draw these rectangles, so let's say I pick from the right-hand side. Some of them are going to be overestimates, some of them are going to be underestimates, because my curve isn't increasing the whole time. When we did x squared, it was increasing the whole time, so when we picked the right-hand side, we always had overestimates for every rectangle. But not all curves are going to do that. So we just have to pick, but as n goes to infinity, it shouldn't matter if I use the left-hand side or the right-hand side because they're going to match. So let's call this x1 and this x2, and then I'm going to put dot, dot, dot because I'm putting a break in my graph. Let's call this one x sub I. Okay, that's just my index for which x value I'm looking at. Then the width of each of these rectangles, we're going to say is delta x. It's however I break up my x-axis. And then the height of my rectangle will be my function evaluated at x sub I. So since I picked the right-hand side here, we could say r sub n is equal to the function evaluated at x1 times the base of delta x plus the function evaluated at x2 times delta x plus all those x values in between going up to x sub I. And we can write this using summation notation. So I can say this is the sum from I equals 1 to n of f of x sub I times delta x. Then my area would be the limit as n goes to infinity of the sum from I equals 1 to n of the function evaluated at x sub I times delta x. And when we take the limit as n goes to infinity, it doesn't matter if I do a right sum, a left sum, or even a midpoint sum. We should get the same value for all of them once n goes to infinity. So we write that as the area equals the limit as n goes to infinity from I equals 1 to n f of x sub I with an asterisk. The asterisk means it could be left, it could be right, it could be midpoint, it could be whatever x value I choose. Whatever sample point on the x-axis I'm choosing to evaluate my rectangles at, to find my heights. And this right here, that part of it, is called a Riemann sum. It's named after some German mathematician. So the asterisk, the x by asterisk means it's whichever x values I decided to use to get the heights of my rectangles. And f of x by asterisk is the y values or the heights of my rectangles to go with it.